Hello and welcome to today's Innovation Coffee Break. My name is Tobias. I'm product engineer at DSpace and I'm focusing on FPGA technology.
And my name is Alexander. I'm product engineer at DSpace, responsible for Scalexis systems. In the last Innovation Coffee Break about DSpace FPGA technology, we gave you a brief overview on the different systems we are offering in this field. Today we will focus on how these systems can be used.
One topic which is often addressed by customers is the enormous effort which is needed for implementing FPGA designs in hardware description languages. Is there anything DSpace can offer in this field? Indeed it is. Let's see what we can offer. Our toolchain mainly consists of two parts, the implementation and the experiment software. The implementation software configuration desk allows creating real-time applications for a DSpace real-time system, and the experiment software control desk is for operating your real-time applications. As a basis for the implementation, we use the well-known Simulink environment, just for programming FPGAs instead of processors. So, for example, there is a FPGA-specific block for multiplication. As a second tool, we use the Vitis Model Composer from the FPGA specialist Xilinx, which brings us specific Simulink blocks for creating FPGA designs. This tool will be running in the background. We simply make use of this technology. The third component is the DSpace FPGA programming block set, which takes over control, ensures proper interaction of the tools, and allows easy access to I/O resources. As a last step, DSpace Configuration Desk is then used for combining the FPGA application with the process application, before Control Desk provides an easy and comfortable way to monitoring and, if needed, for debugging. Let us now show you the solution we came up with.
What Tobias is showing us is a small demo using FPGA block set. It simulates a PI controller. The reference inputs are read from the processor, the control variables is written back to it. What you can see is that the whole model is implemented in Simulink. The FPGA block set is offering an interface for data transfer between FPGA and processor. When setting up a new FPGA model, typically the first step is placing an FPGA setup block within the model and to configure the FPGA platform within the drop-down menus. As next step, we'd like to extend the existing demo by generating a sine wave from the FPGA and outputting it through an analog output. Therefore, Tobias is placing a sine block and I/O write block within the model and assigns it to a specific channel. Then he connects both blocks. Your benefit is that you will not need to program HDL code, but if you want to, you can. System Generator allows integration of HDL code. The procedure is like S-function programming. When FPGA models are getting more and more complex, you probably would like to verify if the FPGA application is operating as intended or to debug application when something is not operating as expected. Since 2022, the FPGA block set is offering a mighty tool for this purpose, the FPGA scope. What is the FPGA scope? The scope allows live monitoring of FPGA signals at full FPGA rate directly in Control Desk, comparable with an oscilloscope. You can connect multiple signals with the scope and decide at runtime which of these you like to monitor. If you need less signal than the block offers, no problem, just leave the ports you don't need unconnected.
Now, how can I make use of the scope? As you can see here, the scope allows a connection of various signals and an explicit trigger. As you can see here, you can simply connect the signals you would like to observe with a block. Within the FPGA model, you will only configure the depth of the scope, the rest can be changed at runtime. For bringing the application into a DSpace hardware, an FPGA build needs to be performed. This can be invoked from the FPGA setup block. The result of this build integrates into Configuration Desk as a custom function, as you can see here. What will also be done within Configuration Desk is modeling the communication between the FPGA and the real-time application. The handling of the FPGA application as a whole is identical with handling of built-in I/O functions, which are available for various other channel types. What you can see at the screen is that I am drawing connection lines between the FPGA and the processor, which represents the communication. The next step will be building the real-time application, which integrates the FPGA application into the real-time application automatically. For running this real-time application, we switch to Control Desk. I prepared a little layout which already allows visualization of the real-time application. What I would like to put a focus on is how easy the scope can be used within Control Desk. Therefore, I simply create a new layout and take a scope instrument from the library. This just needs to be linked with a scope we implemented beforehand. Then, a plotter instrument with direct access to the connected signals will be created automatically. The instrument allows the configuration of multiple helpful options like downsampling. Within the plotter, you can reconfigure the signals to be plotted at runtime.
We hope this Innovation Coffee Break gave you a brief overview on how an FPGA application can be created and how it's operated. Of course, there are much more options in our DSpace toolchain. Within the next coffee break, we will give you a brief introduction into various add-on solutions we are offering for addressing specific use cases.
DSpace, your partner in simulation and validation.